All right, think about this for a second. Over here, you've got the world of mathematical logic. It's a place of pure reason, abstract proofs, and this, deep quest for absolute, undeniable certainty. And then, way over here, you have the world of computer programming, a super practical world of algorithms, execution, and just building software that actually works. For the longest time, these two worlds felt like they were on completely parallel tracks. They had almost nothing in common. But what if? What if they were secretly two sides of the very same coin?
Now, this isn't some philosophical riddle. This is a real question, and the answer to it completely changes how we look at both logic and code. It points to this really deep structural connection between the act of proving a mathematical truth and the act of writing a computer program that runs.
Let's break it down. The world of logic is all about establishing truth. It's about using pure deduction to arrive at something that is unshakably certain. It's about being true. But computation? That's about creating algorithms that do something. It's the messy, practical world of building systems that are functional. It's all about doing something. Seem pretty different, right?
Well, then a discovery was made. It was kind of like finding a Rosetta Stone that lets you translate directly between the language of logic and the language of computation. And I'm not talking about some vague philosophical similarity here. I mean a deep, structural, one-to-one correspondence. A hidden bridge.
This bridge has a name, and it's a cool one, the Proofs as Programs paradigm. You might also hear it called the Curry-Howard Correspondence. It was really laid out clearly in a paper that W.A. Howard circulated way back in 1969. And that paper dropped an incredible bombshell of an idea, that a mathematical proof and a computer program are, in a very, very real sense, the same exact kind of thing.
So, how direct is this mapping? Check this out. In logic, you have a formula, like a statement that can be true or false. In computation, that's a type, like an integer or a string. And here's the kicker. A proof of that formula is literally a program of that type. Think about that for a second. A proof of the statement, if A, then B, isn't just like a function that takes an A and gives you a B. It is one. The correspondence is that exact. It turns abstract logic into code you can actually run. So you might be thinking, okay, that's a neat theoretical trick. But this was so much more than that. This correspondence kicked off a revolution. It totally reshaped both computer science and logic by making these really abstract ideas powerfully practical. So let's talk about the impact. This whole paradigm became the foundation for tools we use today. We got what are called proof assistants, basically software that can check incredibly complex mathematical proofs for errors. It's the core idea behind logic programming. And you know those powerful type systems in modern languages that catch your bugs before you even run the code? Yeah, you can thank this idea. It even supercharged the whole field of automated deduction, letting us build programs that could find proofs all by themselves. Now, the initial discovery was a perfect fit for a type of logic called intuitionistic logic, where every proof has to be a direct construction, which, sounds a lot like an algorithm. But the idea didn't stop there. Researchers like Michel Paurigut here worked on extending it to classical logic, the logic we all learn in school with things like proof by contradiction. This was a huge deal because it opened the door to modeling even more of the complex things we do in programming. And that brings us to the frontier. See, the proofs as programs paradigm isn't just some dusty piece of history. Nope, it's a living, breathing, evolving field of research that is still pushing the boundaries of what we can do in both math and computer science. You can actually watch the idea grow up over the decades. It all starts with that spark in 1969 with Howard's paper. Then, almost 20 years later in '87, Jean-Yves Girard introduces linear logic, which is this whole new way of thinking about logic as a system of resources, an idea that's, super relevant to computation. And then, like we just saw, by 1993, the paradigm gets expanded to classical logic. Every single step revealed deeper connections and unlocked brand new possibilities. So, all of this leaves us with a final, really powerful question. We've seen how this one idea connects the search for logical truth with the act of creating working code. So, if a proof is a program, it means we can use our computers to help us with mathematical discovery in ways we never thought possible. But maybe even more important, it means we can use the absolute rigor of logic to build software that is provably correct. And that's the future this paradigm is pointing us towards, a world of truly trustworthy software built on the unshakable foundation of logic itself.